Welcome back, and thank you very much for watching this lecture video. In this lecture, I'm going to tackle how to figure whether one molecule is aromatic or not. We're talking about electrons, pi bonds, and we said the electron can be treated as a wave, and any wave, it has phases. A phase, it can be positive or negative. Here, the phase is positive, there is negative. When the phase is changing a sign, we say we are passing a node. And so what's a node? Node is anywhere that the sign of the wave, it will change from positive to negative. And node, there is zero chance to find electron. And so node is a place that we have zero chance to find electron there. And center of any orbital, it will be the nucleus. And inside the nucleus, we do not have any chance to find electron because the electron is supposed to be out of the nucleus. So for example, for s orbital, center, it will be the node, and that's going to be the nucleus. There is no chance to find electron there. For p orbital, we have a node. And again, node, it will be the center of the orbital or the nucleus. One phase, it will be positive, and the second loop, it will be negative. For the d orbital, we have two nodes. We call them two angular nodes. One node is going to be here. This is one node. And this one is going to be one node, and the second node is there. So we have two nodes, and they are changing the phase of the orbital. Okay. Now, how do I figure number of nodes? Number of nodes equal to n minus 1. And what's the n? If you know which orbital you're talking about, for example, if you know the orbital is a 2p orbital, in that case, n is equal to 2. So you say n minus 1. N minus 1. In this case, n is 2. 2 minus 1. We have one node, and this node is going to be here. So we have one node, and that node is splitting the p orbital to two lobes, positive and negative. This orbital is aligned with the z, so we're going to call it pz orbital. Okay. So now that you know the orbitals, and let's write electron configuration of nitrogen is 1s2, 2s2, 2p3. Forgive me. Nitrogen, it has 5 valence electrons, so 2 plus 3, we get 5. And last p orbital, it has 3 electrons in it. Each orbital is singly occupied. S orbital is already fully occupied, and it has 2 electrons in it. So in order to make 4 bonds, for example, with nitrogen, we need to somehow make one orbital and empty and like a half occupied, or we're going to have an orbital that is taken by valence electrons, and that orbital is going to be it's going to show up technically as a lone pair. Okay, let's tackle pyridine molecule. Is pyridine molecule polar, aromatic, yes or no? Let's check the pi bonds. The pi bonds, we have 1, 2, 3 pi bonds. So 3 pi bonds means 6 electrons. So are we following this formula, 4n plus 2? And I go 4 multiplied. If I go with 1 plus 2, that's going to be 6. Okay, so we are following the formula for n plus 2, and the molecule, it has 4 electrons, so 3 pi bonds, my bad, 3 pi bonds or 6 electrons. So the system until now is following the the Huckel rules for rules or Huckel formula. Okay, next one is it planar? Yes. Is it cyclic? Yes. How about the hybridization? Let's go after nitrogen. Nitrogen, it has nitrogen is going to have sp2 hybridization. Why sp2 hybridization? Okay, so nitrogen is going to adopt this hybridization. It will use 1 from s and 2 from p orbital. It will give us 3 orbitals of s1 and p2. Why 3p orbital? Why 3 hybrid orbitals? So here you go. Nitrogen is going to have 3 hybrid orbitals. And remember, nitrogen has 5 valence electrons. Out of those 5, is going to use 1, 2, 3 of them. Okay, 3 of them to put them inside sp2 orbitals. Okay, now what do we do with those sp2 orbitals? Next step, we're going to make interaction with neighbor atom. And neighbor atom, like carbon, it will go with opposite spin, and that's going to give us sigma. So we got 2 sigma bonds. Okay, and out of 5 electrons, we use only 3 of them. So what do I do with the rest of them? I have 2 more, okay? 2 more. What should I do with those 2 more electrons? Okay, I can accommodate 1 more here, okay? And now that sp orbital will be fully occupied. So what will happen? It means that orbital cannot be used to make a sigma bond. This is going to be a lone pair, okay? And where is the last electron? Last electron, it will be inside a p orbital. I'm going to show it here. So we have a nitrogen atom. We have a nitrogen atom that it has a p orbital, and that p orbital, it has 1 electron in it. So nitrogen, it can use that p orbital to do interaction with carbon. Okay, remember, carbon also has sp2 hybridization, and then it has 1 p orbital that it has is singly occupied. So we have a carbon, that it has one p orbital that is singly occupied. Now those two atoms, they can have interaction and they will give us a pi bond. Okay, so each p orbital, it has one electron in it. We have 6 electrons, 6p orbital. So that's that compound. It can be aromatic. How about the lone pair? Lone pair is perpendicular to the p orbital, or technically to the ring, is perpendicular to it. So it's not lined with it. This one is pz. You can call this one px, py, or say line with x or y, whatever. It's perpendicular because it's not involved with the conjugated system, the pi conjugated system. We say it has nothing to do with the aromaticity. Okay, it has nothing to do with the aromaticity. So how do I figure whether pyridine is aromatic or not? Okay, ask yourself, how many pi's I have? 3 of them, means 6 electrons. So it's following for n plus 2. Okay, nitrogen has 2 more electrons. What should I do with them? Ask yourself, if I add them to the ring, am I gonna violate the Hooke's rules? Am I gonna pass the 4n plus 2? Okay. If the answer is yes, then keep the lone pair out. Keep it out. Why? Because the system will not technically ignore the aromaticity. Aromaticity will make the system stable. Okay. So nitrogen is gonna say this. Look, I'm already aromatic. Why on earth I should bring the lone pair inside the ring and mess with the aromaticity? So let's keep the lone pair out. If we need it, we will bring it back. Okay. If we need it. So in this case, that one is out of the system and is not gonna get involved in technically aromaticity. But if pyridine is supposed to react with acid, now you can use that lone pair and, for example, react it with H plus, and then H plus it will react with this lone pair and will give us NH. So that lone pair is useful whenever we want to take H from acidic solution. How about this molecule, pyrrole? And in this case, we have 1, 2, so 2 pi bonds. That means 4 electrons. Okay, 4 electrons until now. We are short of 2 electrons, 2 more electrons to get 6. In that case, we will be falling for n plus 2. Okay, so nitrogen is going to say, do I need to use the lone pair to get the aromaticity? Yes, we need it. Okay, we need that one. So in this case, the lone pair, it will be part of the ring. And each carbon, it will have 1 electron inside the p orbital. So we have 4 electrons from 4 carbon atoms. Each carbon, it comes with 1 pz orbital. Okay, pz orbital. So nitrogen, it will put those two electron lone pair inside a p orbital that align with z. It has to be aligned with the p orbitals of carbon. Okay, and you might say, wait a minute, the hybridization of nitrogen is something else. So how come we are dealing with pz? Okay, let's tackle that one. So nitrogen, if you looked at it, it has 3 sigma and 1 lone pair. So 3 sigma plus 1 lone pair, I get 4 pair. Hybridization supposed to be this: 1 from S, 3 from P. We get 4 sp3. Okay, if you get sp3, that's going to be tetrahedral. Okay, and tetrahedral is not, okay, it's not planar. And if it's not planar, your molecule will not be your molecule will not be aromatic. Okay, so how can we make the system aromatic? Okay, and the way the system is going to be aromatic, nitrogen is going to adopt this condition. So nitrogen is going to say, okay, let's adopt sp2 hybridization. Okay, so nitrogen, it will get sp2 hybridization, 1 from S, 2 from P. We get 3 orbitals of S1, P2. Okay, S1, P2. Okay, so we got 3 orbitals. Those are sp2. Okay, and each one, we're going to put 1 electron in it. Okay, now we're going to use this one to interact with the outer atom, for example, methyl, hydrogen, or whatever. So that's its hydrogen. So hydrogen is reaching from here, and rest, they will be carbon atoms. So that's going to be carbon, carbon, and they will come with opposite spin. Okay, now We made 3 sigma bonds. Out of 5 electrons of nitrogen, we use only 3. Okay, we are left with 2 electrons, and nitrogen had the 3p orbitals. We used only 2 of them, so we are left with 1p orbital and 2 electrons. Where should we put those 2 electrons? Those 2 electrons, we're going to put them inside this orbital. Okay, that orbital, it will be aligned with Z, so we're going to call it PZ. Now we were going to put 2 electrons in it. So the hybridization, instead of sp3, it will be sp2, and the p orbital, it will have 2 electrons in it. Okay, why this one, is changing hybridization? If the hybridization is sp3, then your system, it will not be planar. Okay, in order to be planar, we need to have sp2 hybridization. sp2 hybridization, it will be planar. And if you adopt sp2 hybridization, you will have a p orbital with 2 electrons. And those 2 electrons now can be used, and we add them to the 4 to get 6 electrons, and it will be hybrid. It will be aromatic in that case. Again, so how do I figure whether this molecule is hybrid, is aromatic or not? Ask yourself, how many electrons do you have? 4. Okay, do we need to add the lone pair? If we add the lone pair, how many do we get? 6. So lone pair will be part of the ring. In that case, your system will be aromatic. Okay, the system will be aromatic. Okay, how about this too? Okay, for example, oxygen supposed to be sp3, but if you adopt sp3, then it will not be planar. So how about this? Oxygen, it will adopt sp2 hybridization. It will use one of the lone pair and share it with the ring. So now we will have 4 plus 2. We get 6 electrons. That's following 4n plus 2. System is ring, is cyclic. It has 6 electrons. It's following the Hooke's rules. Is a planar, so it's polar. It's aromatic. How about this lone pair? Don't add that lone pair. Okay, why? Because if you add it, you will have 8 electrons. Why on earth you want to add it to make the system to lose the aromaticity? Okay, molecule will not use the second lone pair. Okay, and so this lone pair will be perpendicular to the rest. So this one is aligned with Z. That one is aligned with, for example, X, let's say, or Y. They are perpendicular to each other. And so the second lone pair is not going to help us. Okay, for your knowledge, any atom is going to share only 1 p orbital and to be involved in aromaticity. Okay, only 1 p orbital, not 2 p orbital. So 1 p orbital, it can accommodate 2 electrons. So max use only 2 electrons from each atom and share them with the ring. And so this one, it will be aromatic. That means this one, it will be pointing at. How about this? We have 4. We need 2 more. So this one, it will be part of the ring, and it will be 6. Next one. Okay, let's check. Next one is a good example. Right now, we have 1 here, 2 there. So we have 4 of them. Okay, we have 4 of them. Which one of these do I need to use? Should I use that lone pair or that one or 2 of them? Okay, or 2 of them. So right now, we have 4 pair. If I use this one, okay, if I use this one, I get 6. But then the problem is going to be this one, it will be sp3 hybridization, and it will not be planar. And that's going to violate technically the Hooke's rules. Okay, so if I use the top lone pair, my molecule will not be aromatic. But how about this? Okay, let's use this lone pair. Okay, let's use this lone pair and add it. So we get 4 plus 2, we get 6. Now, what should I do with the second lone pair? That lone pair, it will be perpendicular to the ring. It will be outside of the ring. So this one will be outside of the ring. And because it's outside of the ring, it will not be involved. So I'm not going to count that one. So I'm going to say this one, it will be aromatic. And the second lone pair, this lone pair is not going to be part of the conjugated system. That means that lone pair, it will be available for acidic H.